All right. Next up, we have Oscar Smith and Jameson Nash from Julia Hub talking about memory in Julia. Take it away.
Uh, Hi, everyone. I'm Oscar.
Hi, I'm Jameson.
We both work for Julia Computing. I do mostly ordinary differential equations stuff.
I do mostly compiler development.
And this was the result of me bugging him for about 3 months to do some language development stuff with me on this until I nerd sniped him sufficiently.
Yeah.
So this talk is about the new memory type in 1.11 and the new array implementation that comes on top of that. So the first natural question is, what's wrong with array? And there's a couple issues that are kind of fundamental to the current design. So array is resizable, which means every time the compiler, or every time your code looks up the size, the compiler has to make a new check to see if the size changed because someone might have changed the size. And also, the fact that there is a size and it can change means the compiler or the array has to store the size in memory. And if you push or something, you have to store extra space so that you don't get quadratic performance when you push repeatedly. And so all of that means that there's a little bit of extra memory overhead. It works out to about 2 words, which is 16 bytes on a normal 64-bit OS. Also, because array used to be a special internal, not normal type, all of the array resizing functions that have to look at the internal data to the array had to be written in C. So push and push first, and pop first, and insert all together were about 400 lines of C code. And writing C code that works with Julia objects is not easy, especially if you want it to not segfault when you run garbage collection and stuff like that. And so this code was not particularly well optimized, and as a result was kind of slow. And then the last thing that was less of a problem, but more of a thing that we wanted to add that we didn't have a great way of adding, is that when you're doing some multi-threaded types of computations, it's very useful to have per element atomic operations. And this was a good place to add that. And if you want to, after this talk in more detail, see the design doc that we wrote for this and we're working off, it's linked here. It's about 3-ish pages. And so yeah, now here's what a memory is. Memory is a one-dimensional list of objects. So it is not, as a surprising number of people that we talked to about it originally thought just uint8s. So you have a memory T, so it's a memory int or a memory ordinary differential equation solution. If you want just bytes, that's a memory uint8. This is because types are very useful for compilers to optimize things, and if you make the low level just be bytes, it makes the compiler very mad at you, and a lot of the optimizations you want to do become invalid. Memory is also a fixed size type, so unlike array, it is not resizable. If you want resizability, that's what array is for. But the size of the memory is not one of the type parameters. It is just dynamically stored. The reason for that is static arrays.jl is very useful for some situations, but it's not what you want to build most higher level abstractions on top of. And then the last thing, which is a little bit weird potentially, is that memory supports wrapping foreign memory. So if you have an array in C or an array-like object in Java or C#, you can turn that, you can wrap that in a Julia memory, which is necessary for some forms of interop. And so the layout is very simple. You have your first field, which is just your length. You have a data pointer. If it's a Julia memory, that data pointer will just point to the next byte after that, and then you'll have your elements in order. And if it's a foreign memory, then you will instead point to some arbitrary pointer that's separate. And then the one other thing that isn't shown here is for bits union. So if you have a memory union int comma nothing, for example, after all of the data, there will be a bunch of byte selectors that tell you which type each of your elements are, which is similar to how array works, but again, simpler because it's one-dimensional. And so now with this, we can build up a new array struct using this. And now array is just a mutable struct. it has a ref and a size. The size is the easy part. The size is just a tuple with the size along each dimension. And then the ref is another new type of object called a memory ref, where the memory ref has two fields. And conceptually, you can think of it as storing an offset into a memory. So this stores the first element, or the element of the memory that corresponds to the first element of the array. And this is because arrays in Julia are resizable from both ends. So both you need a length of the array, if it's a vector, that tells you how many things past the end are free space, but you also have the first one, which is the first element of the array, so that if you go before it, everything works out. And so memory ref specifically refers to a specific element of a memory. So it's very similar to a gep or get element pointer for those of you who have used LLVM. They're bounce checked on construction, which means that other than the case of a zero-length memory, once you have a memory ref, you always know that it is in bounds to access it. This is very nice for compiler optimization, because if you have a bunch of different accesses to the same element, the compiler can construct the memory ref once and then just do a bunch of accesses to it. So it allows you to separate the code out cleanly without having to do that sort of analysis on the LVMIR later. And so now the most important part, obviously, is how much faster this is. For small arrays, we're about 28% faster to allocate. Funnily enough, this is actually the main reason why I cared about this PR in the first place. In primes.jl, there was an example where factoring an integer was bottlenecked by the speed of creating an empty array, and now it's faster. And similarly, if you don't need all of the fanciness of array, you can actually just use memory. And so comparing an array to a memory for a small size, it's almost twice as fast. And now that we've rewritten push and all of the resizing functions in Julia, those are all about 30%, 40% faster. And dict, so dictionaries in Julia, now can use memory rather than array, because they do their resizing manually because they need to rehash things, and that means that you need to keep both copies around. And so now that dict uses memory, they're about 30% faster to allocate. And so here's that in graphical form. As you can see, these are all some pretty nice benefits. And on the bottom, it tells you exactly the code that was benchmarked. I believe this was all benchmarked on a Mac M2 Pro, something like that.
I think that's what I used.
But it doesn't really matter. It is relatively architecture independent, the speedups. And to implement all this, we have a handful of new intrinsic functions in Julia. So there's you make a new memory, and then you have memory ref new, which makes a memory ref. You have memory offset, which tells you what index of the memory ref is to, and then you have memory ref get and memory ref set that do essentially the get index and the set index, except that because of the memory ref, it's decoupled slightly. So the memory ref get and memory ref set both do not take an index, because the index was constructed in the construction of the memory ref, which simplifies some things a little bit.
And finally, we realized we could take this opportunity as we made a more generic array and simplified all of that code to try to figure out what else could we do with this, and how can we add some ability to leave ourselves space in the future to make it even more general. And as we looked into that, we ended up finding there was basically two independent axes that we were interested in supporting. One of them we call the memory kind. And right now we only have two kinds, either not atomic or atomic. But the exciting part of this is we now have the ability to express to the compiler that we want a memory, but we want it to support all of the atomic stuff. I'll go into that more in the next slides. The other thing is kind of an unusual one, mostly comes to us in the GPU world, that we have the concept of an address space. The GPUs have different kinds of memory, and they can have different characteristics. They can be accessible to different threads, or they can have different performance characteristics. And languages have been starting to add the ability to express that directly, and Julia just hasn't had that ability. So CUDA.jl has had to re-implement a lot of what Array knew how to do already in base, and had to use generated functions for that. And so we're hoping they'll be able to use the built-in memory support now to be able to generate the code that they want on the GPU using all of the existing generic infrastructure that we have. And that's parameterized by module as well. So you can create code and say, like, this is a memory that I specifically want to use with the CUDA package versus memory that you want to use with the AMD GPU package. And they could both hopefully coexist, and the compiler would understand which one you were trying to use at the time. On the CPU, only the core.cpu memory exists, and so that's the only one that you can allocate and use. But when you're targeting these other platforms, the other address spaces become meaningful. And so those other platforms can define how to allocate them. We really needed atomic memory that was slightly separate from regular memory because there's some differences in the constraints on how you need to allocate it. So for example, the alignment that you require is greater for atomic memory. And we didn't really want to just say, like, OK, now all objects have to be aligned such that they support atomic access, because that's very wasteful when most arrays don't need atomic access at all. The other way that they differ is in a way that you use them. When you talk about an atomic memory, we aren't talking about the memory itself remaining any sort of atomic state. The memory itself is constant at a given point in time. But when we do an operation like, say, add 1, unlike normal memory where we'll load that value, add 1, and then store it again, if another thread came in and loaded the value and changed it, well, you were off doing your addition really slowly on one processor, you might lose that intermediate update. And so the atomic memory lets you specify not only do you want to, say, increment that value at that location, but you want to do it in such a way that you don't lose any updates that happen on other threads at the same time. So there's really only one primitive that you must have to implement atomic. That is some sort of modify operation or a compare exchange. The compiler, though, can't always optimize it, given how many things can be expressed with just one compare exchange. So we also have a load, we have replacing, we have atomic store. So we have all these different ways in which you can specify exactly how do you want to use this memory atomically. What exactly are you trying to tell the compiler is atomic about this memory? We added similar things last year. So you can refer to my talk last year on adding it. Add atomic declarations for fields of structs. So if you had a mutable object last year, you could specify that one of the fields or several of the fields were atomic. But now we can have the ability to specify that an arbitrarily sized memory is atomic. And so that should allow us to write some new algorithms that we weren't able to write before directly in Julia. Some more key points about this. So as I was saying, when you specify that the memory is atomic, what you're really specifying is that you want the operations on that memory to support the ability to do them atomically. So that could mean simply that you want the store to the memory to be atomic, so that if you have another load on a different thread that's watching that store, you want to make sure that the loads can only observe values that were ever stored there and not invent a value out of thin air, as it were. Or you might say you actually want to increment the counter such that if many threads are incrementing the counter, you don't accidentally lose one of the increments to the counter. But as we were also doing this atomic work, so had already been looking at this previously with the threads, with the struct part of things, we were looking that there's an asymmetry between reads and writes that we wanted to be able to reflect in this. So when we look at a load of a value, those are always, if you just have multiple threads loading a value, there's no data race necessary. And so you can safely load values from an atomic generally on many threads without really needing to carefully think about what is the intent. However, if you ever have a write or a store to the value, and any thread is doing any other operation on the value at the same time, whether it's a load or a store, that will cause a data race. And a data race effectively just means that you need to instruct the compiler what your intent was and what value it's allowed to throw away or what part of the operation is unnecessary. So to reflect this difference, when you just load the value, the add atomic is optional, so you can specify it, but you don't have to. And if you're stored to it, then you can have to specify add atomic. So for this example on the slide, you can load x of I, assuming x is an atomic memory object that's been initialized and has at least I elements. But when you store to it, you have to write the same x of I equals 1 that you would have written before, but prefix it with this add atomic macro. And if the add atomic macro was missing, or if you tried to use add atomic with an array that wasn't atomic, then you'd get a concurrency violation error at runtime that points you to that part of the code to say this part isn't using atomics where you probably meant to use it. And so that gives you a hint that you need to go look at your code there and see what was I trying to express, what does the algorithm require of me in that point. They're mostly compatible with C11 for is-bits types in Julia. So if you have a plain old data type in C and you have an is-bits type in Julia, those should get pretty much the same alignment. They'll emit pretty much the same compiler processor intrinsics for that so that they could interop. That only works up to about double word, and then we use a different optimization, a different layout than C. So if you wanted to just interact with C, what you actually probably want to do is look at my talk last year where I talk about some of the unsafe load, unsafe store, and unsafe modify class of functions. So those existing functions that work with C pointers have been extended so that you can pass in a memory ordering and specify that you want to use those atomically. So that work actually is already in if you're just looking to interact with a library that's in C. So it really depends on who are you trying to have own the memory and where do you want to manage where this memory is being passed around to different threads. Is it in C or is it in Julia? And finally, I think just another big point here is that Julia wants to make things easy so that you don't have to code differently depending on the properties of the object that you're trying to put in there. So this works regardless of the size of the object, whether it's abstract or concrete, whether it's a union type, and even if there's interior pointers. So if you're just wrapping an object in a tuple, singleton tuple, we don't have to allocate the singleton tuple. Same with the field of a struct. With an atomic field of the struct, we can do the same thing, where there's one or up to about 2 pointers, because that's what hardware support gives us is 2 pointers to be able to do atomically very directly. And then beyond that, we will allocate a lock per element of the array so that it can do still per element atomic operations, but using what's available on the processor. So it can lock that element, do the change, and then unlock that element. Now to go on to some examples. Say we wanted to make a histogram of some computational results. There's basically 3 ways of doing this. So originally, we might have just done a single-threaded approach where we create a large array. Here I'm making a histogram of 400 elements simply of the rand function. So you could plot this afterwards and try to see, is my rand function fair, or what does it do? So I compute the index using the rand function, and then I increment that memory location. This is no atomic operations, and there's no threads here. And so when I do that, it takes about 1/3 of a second over 10 to the 8th elements. Computers are great at doing large amounts of operations very fast. But say that wasn't fast enough for us, so we think, I want to make this faster. I don't have a atomic memory yet, so I'm going to try to just use a single lock over the whole array and see how does that do. And so if we make a single lock over the whole array, we can use our new lockable object to make that conveniently expressible. We could have also used a separate lock from base and allocated those separately, but this just gives us a nice version of that. And then I believe I ran this benchmark on 16 threads on a server architecture Intel machine, but also tested them on MacBook M2 and got similar results. And so I could show that I got the same answer. I asserted that it came out and the sum was correct, so I know I didn't lose any updates from my threads. But suddenly this took 13 seconds instead of 0.3. So we're got a very large number of lock conflicts. I think it's very fun now that we have the lock conflict information, so you can actually see some idea of what was going wrong with this algorithm. And one thing that's probably not super clear is that the plus operation is so fast. Basically, all of the time is spent with the lock trying to update it. Now we can do atomic memory, so we do the same thing, but we're just going to add even more annotations to our code here. So everywhere I had a vector or similar before, now I have an atomic memory, and at atomic, I'm going to initialize it. We don't have as much resources built up right now, so the for loop, for example, I couldn't use the zeros function because it's a store, and I needed to specify when I tried to assign all these zeros to it, how exactly did I want all of these zeros to be assigned into the array? In this case, I gave it the monotonic ordering because I don't really care. I just need it to be filled. It's still a single-threaded object at that time. And then I run the threaded loop, and it takes about a second. So we got some great thread scaling out of this. And this is actually probably what I would expect. We've really increased the memory traffic. These CPUs have to be really chatty to notify all the other CPUs that they have a new value. And then they have to go back. And so there's just a lot of back and forth that really doesn't allow us to get much scaling or get negative scaling here. But in some cases, this will be the right thing that you need. And this is now available and possible in Julia. And is quite a bit faster than the global lock, although it is not as quick as the single-threaded. So one of the takeaways is just that this is not an ideal algorithm. You would just not want to multi-thread it in this way. But it is fast, and it is now possible.
And so for what we learned about this, the biggest takeaway I had from this entire process is that really it was probably a mistake to make array be resizable, and it's way too late to fix. But sometimes there's a fixed-sized array package now that is using memory also as of 1.11. Shout out to Gabriel for primarily doing that. But yeah, just having to deal with resizability is a total mess.
Yeah, part of this work we kind of knew. We could write a lot of these optimizations in C, but it's a lot of repetitive work, and it only handles really specific cases. Once we moved this into Julia, it became much easier to write a really fast push-bang function, and now it's in Julia as well, so we can customize it in Julia. We could evaluate a new over-allocation function and see how that performs, all directly in Julia without leaving the REPL.
Also, language design, it turns out, is really, really hard. This is, I think, the third time someone has made a pull request to try to add this functionality. And it was the thing that ended up getting merged was our third or fourth rewrite of memory, as there's a lot of design decisions that you have to make, and each of them precludes other choices, and finding the right balance of things is very difficult.
And finally, memory models are hard. It's really hard to define what it means to store things into memory. What do you expect when you store it into memory, and how do you explain to the compiler what your intent is as users? So with that, we can go to Q&A. We also have a question for you. Do we try to make a breaking change to make the atomic emoji shorthand for atomic the macro?
Let's have a quick round of applause. Thank you so much. Questions right here?
How does any of that relate to string? Will one day string be on top of memory? And string is immutable and arrays are mutable. Is there a sort of immutable version of memory?
So we've thought about making an immutable memory kind. It is potentially doable. There's some complications there.
Yeah, it's been internal discussions on Slack and different channels that I don't remember which one on there. Looking at the idea that we have the ability right now to make strings, and they sort of swap between the memory and string representation in certain cases. So if you make a I/O buffer, it defaults to making a memory, but it's actually a foreign memory that's backed by a string. So when you're done with the I/O buffer, it can give you back the string that you've already populated.
Also, yes, we
So in
did
some
say
ways,
that that
behind the
wasn't
hood,
allowed.
it
Don't
is
worry about it.
Making a string for you with a memory on top of it. And we're discussing, I think we could make strings more directly convertible from memory, but it opens up questions on what does it mean to be a string if you can change parts of it, and what does it look like? How do you prevent changes when you didn't expect them? So we haven't quite figured some of those out. And then, yeah, as Oscar was saying, one of the other kind of memory that we've thought about using in that type parameter is constant or something of that nature to say, this memory actually doesn't support modification because it's derived from some object that doesn't support modification. And is that, we're trying to figure out, is that useful, and how would we integrate that?
Can we get a fixed size arrays in Julia?
A fixed-sized array, I'm not sure whether we'll add it into Julia itself. We have it in a package. My guess is that might be a Julia 2.0 thing, but we'll see. Depends on demand.
I have to listen to them.
Hello, thank you for the talk. Very interesting here. So I'm just wondering, how does memory work? Is there an abstract memory type? And when you're looking at an array, I think it's really exciting to think forward to GPUs and potentially like immutable types that you might want to use memory for. And so is memory kind of hidden inside? Because it's not in the parameter brackets of like what memory are you using versus GPU array type.
So currently array, array only supports the normal non-atomic CPU memory, just because we don't have type parameters for it. One of the nice things with the fixed size array package is that it does actually support all of the fancy things. So that does support atomic arrays and GPU arrays once CUDA, or once and if CUDA or someone else actually implements those.
Also, so there's two objects. Generic memory is the thing in core that implements everything. Memory is actually a type alias for a generic memory where we filled in the kind as being not atomic and the address space as being CPU. You can make a reference to a type of memory that has a different address space by using the generic memory and then filling those in to specify what kind and where. There isn't support for that in base because it's not a CPU thing. And so we're hoping and anticipating working with the GPU folks so that they can use that abstraction. However, to add more caveats to that, I'm expecting that will be what you run on with the GPU, but you wouldn't actually have an instance of that object on the CPU. So you'd have some sort of indirection objects. You'd still have like a CUDA array object that just tells CUDA where to find that object. But because they're in different address space, like they kind of have to be indirect because it's not on the CPU accessible. So you wouldn't have the object itself.
I have time for one more very quick question.
So I'm sorry if I missed that in the talk. So there's the atomics package with an X, which already adds add atomic for arrays. So is that just using locks so far, or how does it work?
So the atomic X, or however we pronounce it, package, in the past has been using LLVM call, so it has a very limited support on what types it can work with, and it can't correct the alignment of an array. So it works with just very basic primitive int, float. I think there was support in there for some sort of any, perhaps, but GC allocated types were mostly not supported by it. So this is now providing, should be equivalent functionality, but integrated with the add atomic macro in base, and integrated for all types rather than just the specifically listed built-in ones that it could handle.
Also, I believe atomics.jl is going to be getting a PR sometime in the next couple days to weeks to support the atomic memory stuff in 1.11 because due to time constraints, the fanciness only got there in 1.12, even though the type exists in 1.11.
Thank you so much. That's all the time we have for questions. Let's have another round of applause.